Welcome to this talk about the unreliable goodness of fit. This talk is brought to you by DataQ Intelligence and it's part of data quality assessment. And the aim of this talk is to convince you that the goodness of fit is not reliable. It needs to be treated with caution and interpreted with caution. So the goodness of fit is depicted here on the left-hand side, and its definition involves a summation over the indices I, which abbreviates the Miller triple HKL. Summation goes over the difference between observed and calculated structure factor amplitudes divided by the standard deviation of the observed structure factor amplitude squared. And this whole part is squared again. So it's a rather complicated notation here. And the number of observed intensities, that's the number of intensities in the least squares refinement to be more precise, plays a role here as well. From this number is subtracted the number of parameters of the model. So that's the degrees of freedom. Now, this formula doesn't look very appealing, and it can be rewritten in a simpler form if we just divide by the number of observed intensities. We arrive at a simpler form, which is an average. In this simpler form on the right-hand side, the goodness of fit is written just as the square root over the mean squared weighted residual over alpha. So these brackets indicate taking the average over the whole data set. The green entity here is the squared residual, and it's the same entity which is also in this definition, in this traditional definition of the goodness of fit. Alpha is a number between 0 and 1, and usually closer to 1. And it again involves the difference between observed reflections and the number of parameters in the model. Now, in this simplified form, we need to recall that zeta squared are actually supposed to be random numbers, assumed to be random numbers, because this whole definition is actually coming from the chi-square distribution, in which the entities zeta squared are assumed to be identically distributed random numbers. Now let's have a look at a derivation of the goodness of fit, a short derivation to understand its meaning. This short derivation starts with the assumption that delta squared, the unweighted residual, the difference between observed and calculated structure factor amplitudes, squared structure factor amplitudes, is approximately alpha, that's the number between 0 and 1 again, times the squared standard deviation of the observed intensity. So this equation just expresses that it is assumed that delta square can be explained by statistical fluctuations of the observed intensity. And in that sense, it's valid only if there are no systematic errors in the data set, and also if the standard deviations are correct. And if both of these conditions are met, then delta squared is, on average at least, as small as it can be in this data set, as small as possible. Now let's bring sigma squared on the left-hand side. And then we have delta squared over sigma squared for the individual reflection I equals approximately alpha. And this is not an identity, it's a statistical relation and meant to be valid in an order of magnitude sense. It's clear that this entity on the left-hand side can be 0, or it can be 9, for example. If it would be 9, it would come from a residual with absolute value 3. So 3 standard deviations away from 0. So, but in order to arrive at a valid equation, which is an identity, or closer to an identity at least, averaging over the whole data set is done. And then we arrive at equation 3, which states the mean squared weighted residual equals alpha. Again, alpha is a number between 0 and 1, usually closer at 1, as closer to 1. You can replace alpha in your mind by 1 as a simple way to think about it. And then if you need correction, you remember that it's slightly smaller than 1. This equation here and this equation here, they state the same. On the right-hand side, it's just that delta squared over sigma squared is abbreviated by zeta squared, the squared weighted residual. Now, if we look again at equation 1 and see what we have done, it was in a first step to divide by sigma squared, and in a second step by averaging over the data set. Now we can do it differently and interchange those operations. We could do the averaging over the data set first and then bring everything to the left-hand side. And this leads to an equation which should hold under the same conditions. So let's try that and see where it leads. We start again with the same equation 1 as before, but now we do the averaging first. So if averaging is done over the data set, this yields equation 2, and it says that the squared unweighted residual equals alpha times the squared standard deviation of the observed intensity. Now let's bring everything but alpha on the left-hand side. And then this equation just states that mean squared unweighted residual over mean squared standard deviation of observed intensity equals alpha. So now we have two equations, a traditional equation 3 and an alternative equation 3 prime. And what they have in common is that on the right-hand side, they have the same target value alpha, the number between 0 and 1. And the difference between equation 3 and equation 3 prime is that the averaging was done in a different way. But both of these equations should hold under the assumption that there are no systematic errors in the data set and that the standard deviations are adequate. The traditional equation 3 is related to the goodness of fit. You see also in the goodness of fit, if you replace zeta squared by alpha, then the goodness of fit is identical to 1. In a similar way, we can use equation 3 prime to define an alternative goodness of fit. And it's defined analog to the goodness of fit, with the only difference that the averaging was done differently. So it looks quite similar. Now let's have a look at some numbers from published data. You see in this table in the left column, first column, the mean squared residuals. And in the second column, the mean squared unweighted residuals over the mean squared standard deviations of observed intensities. And in this first example, we see that the mean squared residuals is equal to 1, 0.00 within 2 digits. So that will result in a goodness of fit value very close to 1. But if you look at the second number, you see that the unweighted squared residual is 25 times 0.14 larger than the mean squared standard deviation of the observed intensities. And I hope you are shocked by now, or at least surprised, because would you guess that from this number, that from knowing that the mean squared weighted residual equals 1, that something like that would even be possible? I hope you agree that this is not only surprising, but that it also indicates that in this data set there are some severe systematic errors, and that these severe systematic errors are reflected in equation 3 prime, because it leads to this large number. But it's not reflected in the mean squared weighted residual, which is just close to 1 and therefore will lead to a goodness of fit value also close to 1. Let's have a look at the last example here. Here the mean squared weighted residual equals 0.98 and is also a number very close to 1. However, the mean squared unweighted residual equals 0.25 times the mean squared standard deviation of the observed intensities. That means delta squared is on average only a quarter of what we are expecting it to be. So there is some form of severe overfitting here because delta square is much too small. However, this overfitting is not reflected in this number. It's not reflected in the mean squared weighted residual. The problems we see here are not problems of a diffractometer or a diffractometer type or diffractometer producer. You see that differences between equation 3, numerical differences between equation 3 and 3 prime occur also with different other diffractometers. So I need to emphasize that you don't need to look for hundreds of data sets in order to find examples of this kind. Analyze 10 to 20 data sets and you will find those numbers or similar ones. If you want to look those numbers up yourself or or calculate them for yourself, the references for these data sets are given in the corner, in the bottom left corner. So you may calculate the mean squared unweighted residual over the mean standard deviation of the observed intensities for these sets and compare those numbers to the mean squared weighted residual. You can do this on your own, or you can use our web services, because both of these entities are part of our data quality analysis report, which is available via our web server. As a summary, the goodness of fit is not reliable because even when the goodness of fit is exactly 1, it does not mean that there is no overfitting or no underfitting in these datasets. The mean squared unweighted residual can be as large as 25 times larger than the mean squared standard deviation of the observed intensities, and the goodness of fit is still close to 1. So it's not reliable in that sense that you can draw any conclusions from that about the content of systematic errors. It's therefore not a reliable metric for the quality of a fit. The questions here are, why is the GooF not reliable in these cases? And under which conditions is the goodness of fit reliable? You can alternatively ask yourself also, under which conditions is the numerical value between the goodness of fit and the alternative goodness of fit the same? This gives you a lead to the first two questions here. Now, if you find this inspiring, you may wish to find the answers for yourself, or try to, and you're invited to do that. You're also invited to digest what has been said here and to check those numbers for yourself, that there can be such great differences between the mean squared weighted residual and the mean squared unweighted residual over the mean squared standard deviations of observed intensities, despite that these should result in the same value alpha. So let us know what you found out, or just wait for another video where we will treat those questions. Thanks for your attention. If you need some literature dealing with this alternative goodness of fit, here are two citations given where you will find some of those formulas again. We are DataQ Intelligence, and we are into the topic of data quality questions in diffraction data. Thank you for watching. Bye.